Now we'll see the magnetic field due to a solenoid and a toroid. What is a solenoid? What is a toroid? We'll just understand. Up till now, what we know is what is Ampere's law. Just giving you a brief recap so that you understand this in a better way. Ampere's law said that this BdL is equal to mu 0 into I enclosed. This is your Ampere's law. So what is the meaning of this? The meaning is, let's say we have a closed surface, the length of which, if you start from here and you calculate the length and it comes to, let's say, L. What is this L? This is from here to here. If this is L and we have several currents crossing this, let's say I1, I2, I3, then the magnetic field due to this is B into L, that is complete L, L that is mu 0 into I enclosed, I1 plus I2 plus I3. Simple. This is our magnetic field as computed from Ampere's law. And I told you how to, what is the magnetic field due to a circular loop like this. If you have a circular loop and current I is through this, what will the magnetic field intensity at this point? This we have seen, we have calculated using Bardsworth law, we have calculated using Ampere's law. So this is the basic concept that we need to know when we want to know what is a solenoid. So now let's get to solenoid. What is a solenoid? Let's say this is a cylindrical surface and wires are wound around it. The winding is like this. This is called solenoid. Clear? Now let me show you. This is a cylindrical surface. What you do, this is wire. Let's say this is copper, pure copper. Now what we do, we wind it like this. See. So when you wind it like this is in a cylindrical form. See, this is in a cylindrical form. This is solenoid, nothing else. Now, if you look at this particular solenoid, let's say the number of turns here is only 10, 12. Let this be up to this length. Then what will happen? The radius of this circle will be far less than the length of the whole solenoid. So that is what we require in a solenoid. That the length of this solenoid. What is the length? This length. This. If it goes up to this, for this the radius and length are appreciable. Radius is not very less than length. But if this goes on, the winding goes on like this, and this is up to this point, then this will be, the radius will be far less than the length of the solenoid. So it is required in a solenoid that your the radius is far less than the length. Okay. Now let's understand. We have seen, if this is a circular loop, we have seen we get magnetic field at, if this is the circular loop, at this distance we know what is the magnetic field, the strength of magnetic field P. We have calculated it. So there are several turns. So because if the magnetic field at this point, because of this one turn is B, then what is the difference when we have a single this length coil and we have several coils? The difference is that I will now become Ni if the number of turns is Ni. That is, one I is in this, one I is in this, one I is in this. So we use Ni in place of this. So this is a solenoid, and when you just rotate it like this, so that the number of turns is very less here. If it is a circle, that is, it forms a circle, then it is called toroid. Like this. If let's say we have like this, and the spacing is very close, I have given very, the gap is very large, not large. If this is very, very close gapping, it forms a loop, then it is called a toroid, and this is a solenoid. So what is a solenoid and what is a toroid? You understand? Now let's do the mathematics on it and let's find out the magnetic field, the strength of the magnetic field. So first of all, let's talk of solenoid. You know what is solenoid? If you look at it, if you look at the windings, it will be like this. One winding to this side, like this. See, this, then this, then this, then this. This is how the winding will be there. If you hold the solenoid in your hand, these are wires. Let the gap between them be very small. Now what happens? You know, this is actually, it is a circle. So you don't have any magnetic field outside the circle. Why? We have discussed this when we were finding the magnetic field strength due to a coil. So where you will find magnetic field strength? In the inside of this pi r square, this area. Okay, this is the first thing. That is, you don't have magnetic field outside of this. You have magnetic field only inside. Okay, that is, this is, you'll have magnetic field due to this coil, this wire. You'll have magnetic field due to this coil, that is a circular loop, due to this. So they'll add, and you'll have magnetic field in this only. Okay, inside the solenoid only, inside that cylindrical shape only, you'll have magnetic field. Now actually it is like this, at the outside it is like this, but if you take a small cross section, it is, you can assume it to be fairly parallel. What will be the direction? You know, if the direction of current is this, see, this is the direction, I is revolving in this direction. So what will be the magnetic field? See, I is in this direction. You can take I in this direction, like this. It is moving. Then the direction of magnetic field is to this side. So magnetic field direction is this side. That is direction. Okay. So where do you have a magnetic field? Inside only. You don't have magnetic field out of this. You don't have magnetic field out of this. One more thing. What about magnetic field between the two wires? You'll have certain magnetic field between, due to the wire just close to it. What happens? See, this is going this side. So you have one magnetic field. If this magnetic field is this, due to this wire, it will be this. So this actually cancels out. That is, due to this you have magnetic field into the wall, and due to the second one it is out of the wall. So these two cancel each other. So finally you don't have any magnetic field between the gaps also. So finally the magnetic field is within that cylindrical shape only. Clear? Now let's calculate it. Let's say this is the cylinder. Okay, this is the cylinder. Now you have wires like this, the windings, that is here to here, here to here. I'm not drawing that. Let's say we consider a small section, this one. Why? Because we have to take B dl equal to mu 0 I. This we have to take. So we need to find the dl, closed loop. So we have a closed loop like this. Let this length be L. Okay. What is the current? Current inside it is I is, let N be the number of turns per unit length. So the total number of winding is NL, and let the current carried by one wire is I. So total current enclosed inside this, that is, if you have NL number of wires and every wire is carrying I current. So total current enclosed is NLI. Clear? Let me explain this again. Let I be the current flowing. Okay. So it is flowing like this. Let N be the number of turns per unit length, and L is the length under consideration. So what do you get? The total current will be current flowing into the number of turns per unit length and the length. So here you get IE. So mu 0 I. So our I is clear. Now let's see what is C. This is this length along, let's say this is A, B, C, D. So along AD and BC there is no magnetic field because this is circular loop. So parallel to this loop, parallel and anti-parallel, you don't have any magnetic field. This you know, that will be 90 degree. So it is 0. You can have magnetic field this direction or this direction because then it is aligned to this. What about this? Magnetic field into this length? 0, because magnetic field out of this solenoid is 0. Magnetic field, you don't have magnetic field here. So you have magnetic field here only. Now this is a closed loop. magnetic field here is 0, this, and here is 0. So finally what you get is this closed loop dl. What you will get? Here you don't have any magnetic field, here you don't have any magnetic field, here you don't have any magnetic field. So your this dl will be actually L only, this length only, along this length only. Try to understand. We are using a closed loop, but we don't have magnetic field anywhere else. We have magnetic field along this line only. So B into L, and this is equal to, as per Ampere's law, it is mu 0 into I enclosed. This is mu 0 N L I E. This is B L. So L cancels. What you get? You get the magnetic field is mu 0 N I. This is the expression for the strength of magnetic field. And I told you the thumb rule to find the direction of the magnetic field. So this is about solenoid. Clear? Now let's talk of toroid. The expression here is B is mu 0 N I, where N is the number of turns per unit length, I is the current flowing. Okay. Now let's talk of toroid. I'm redrawing the picture. I'm redrawing the picture properly. Let's say this is our toroid. So what will happen? We'll have winding across this circular cylinder. It will be like this. The gapping will be lesser, but just for your understanding, I am drawing it. Okay. So this is your toroid. What will be the magnetic field out of this? 0, because if you consider one circle, circular loop, here magnetic field is 0. So here magnetic field is 0, here magnetic field is 0. Simple explanation. Also, even if you try to find out magnetic field here, you take a circular loop. What is the current flowing through it? It is 0. So mu 0 into 2 pi r will be, if the radius is, let's say, r, so B into 2 pi r will be mu 0 into I enclosed, that is 0. So magnetic field here will also be 0. Clear? So you don't have magnetic field here and inside this or outside of this. So where do you have magnetic field? You will have magnetic field inside this circular cylinder. Let's use this term. So if the radius of this, the average radius is, let's say, r, then what you will get? You will get B into 2 pi r. This is the length. This is equal to mu 0 into I enclosed. What is the I enclosed? What I is enclosed here? Let's say the total number of turns is n, and the current flowing is I. So what you will get? You will get mu 0 total number of turns into I. So this is the expression. So the expression for B will be mu 0 N I by 2 pi r. So this is the expression for magnetic field strength due to a toroid. Now, if you take n, small n, that is number of turns per unit length. If you take this, then what is n? N is total number of turns. Total number of turns will be 2 pi r, this is the length, into n. N is the number of turns per unit length and total length is this. So you can say n is 2 pi r n. Now put it here. This will be mu 0 2 pi r n I by 2 pi r. This cancels this. So what you get? You get mu 0 n I. So it's very interesting. The expression for toroid, magnetic field strength in a toroid is same as it is in solenoid. So this is a very interesting thing. So I think you must have understood what is a solenoid, what is a toroid. Okay.